So okay, let's first look at how to construct neural networks. We already see that how to construct multi-layer perceptrons in the previous lectures. Here, we define a sequential network, which is a container, and adding 2 dense layers. The first dense layer have 256 output, and using ReLU as the activation function. Then this is the output dense layer. The output dimension is 10. Okay, and in the forward pass, we generate a random variable x. You have 2 examples here, and the input dimension is 20. Each example have 20 features. We initialize the parameter for the network and feed x with the input. We can get the output y. We can print here. So because the last dense layer have 10 features, we know the output will be 2, which is number of examples or the batch size, and 10, this is the number of features on the network. Okay, that is what we already see. Now let's re-implement the same multi-layer perceptron, but with a customized block. If you're using PyTorch before, it's pretty similar. So what do we do here? We create a customized class, MLP, which is a subclass of a thing called block. Then this class have 2 functions. One's called init, one's called forward. In the init function, there's 3 lines of code. The first function we call the superclass, which is the unblock, called unblock initialize functions, which is kind of initialize the data structures used by gluon, and we can the gluon later on can let you to initialize properly. Then the major purpose of init function is to define, to create all these layers. We're going to use the ladder. So here we create a hidden layer, similar as what we had before, and we create another output layer, is another dense layer. Okay. So the forward function, we are defining how we compute the network. Given the input x, this is an ND array, we first give it to the hidden layer to get output of the hidden layer, and then get output, and then feed into the last dense layer, get output, so return the results. So 2 functions, init define the parameters, forward function define the forward functions. Okay, so to use it, it's very similarly, we create an instance from MLP, and then initialize the parameters, and feed x, we get the results. So it's very similar to for sequential before. So if we run this one, we're going to run the net forward functions. Now, using the unblock, we can implement the thing very similar to unsequential before. Here we call it mySequential. So mySequential function is a subclass of unblock, and it is initialization. We don't have any layer yet. And we define the add function. Every time we can add a layer or block, we call it a block. So what do we do here? So the unblock function have a thing called children, which is a dictionary to store all these layers we have. So for given any block, which is a layer or could be another network, we assume it has a name. It's a string name, and we store the string name is a dictionary given the string name and store into children. So then in the forward function, what do we do here? We iterate over the dictionary. And for each block, given x, we just evaluate it. Because children is ordered dict in Python, which means the traverse order will be same as the one you how to add into the dictionary. So depending on how you add each layers, here I'm going to call these layers one by one and get the result and return x. Okay. So to use it, it's very similar to sequential before. We first create an instance here, and then adding a layer, a hidden dense layer, adding up layer, initialize it, and run the forward function. So basically, we use unblock just to re-implement unsequential here. The reason why we're going to use the unblock because, well, it provides you a lot of flexibility to how to define network. For example, here we do a fancy MLP. Even I don't know if it can train any meaningful result, but I just want to show that you can write arbitrary code in the unblock. So in the ended function, I do two things. Firstly, I create random variables, random parameters, but I don't want to update these parameters. So what I do here, the unblock have a parens. We're going to show the parens later, a parens to store the parameters, and we can get constants means these parameters we are not going to updating. So it's going to fix during training. So we are not going to compute gradients. And then it's a name. We're going to talk about name a little bit later. Given the random uniform, it's 20 by 20. So this is random weight. Another one is like it's a normal dense layer. Like output is 20 and ReLU as activation function. Now, the interesting thing is on the forward function. So given x, we first input into dense as normal. Then here is another dense layer. What do we do here? Given x, and we get the random weights and dot data to get the data, and the bias is 1. It's just a constant, and perform the ReLU here. So basically, this is a dense layer with parameters, with the random parameters we generated before, and one bias layer. And this dense layer will not get updated during training. Question? No. Then another interesting thing here, the third layer, you just reuse the dense layer, which means the first dense layer and the third dense layer share the same parameter. So when you compute the gradients, we first compute the gradient with respect to the third layer, and then with respect to the first layer, and to the parameters, the gradient is just a sum over these two layers. Okay? And then also have some y and if-else conditions here. Y, we already showed the autograph in a notebook here. Y in long is larger than 1, I just reduce it. And y, if it's too small, I just multiply it. So this for function can be writing arbitrary code here. That's hard to make for the sequential interface. Question?
Why do you not want to update the randomly?
Just for show, you can do that. Sometimes if you do fine-tuning, we're going to show a later, which means you grab a network from the previous, train on another data set. I just want to train a few top layers. I'm going to fix the parameter at the bottom layer so that because my data set is too small, I don't want to overfit the network too much. So I can fix a bunch of layers, that one. Also, you want to do module training. You have pretty fancy network. Every data set, multiple data set come in. Each data set only train a part of the network. Like you can do a lot of fancy things. Okay, but usually don't do that. Yeah.
Why do our blocks not carry around information like the trainer or the training history?
Okay, so the reason is because block only defines the network and the parameters. That's all. And the trainer, we're gonna using the network as an input and do updating. So that's just the design decisions. Like the block only have parameters and the definition of the network. So because the reason is because if you do inference, you only care about block. You don't care about the trainers. Okay. Then the fancy MLP, similarly as before, like you can create an instance, run the initializations, and run the forward pass. That's as normal as before. The last one, like we can mix all the things together. So no matter it's a layer or it's a customized block, a customized NLP, or just unsequential, all of them is a subclass of unblock. So we can mix all of them together. So here we define an MLP, another MLP. It have a network. It's a sequential network, 2 dense layers, within it. And another is just a dense layer. For the forward function, given x, we fit into to net and to dense. So this MLP contains unsequential and also a single layer. Then we can also do like we create a network. It's a sequential, and we put it into last MLP into the first block, and then another dense layer in the second block. And finally, we can initialize another fancy MLP as the last layer. And this one is still like you can initialize and get X to compute results. Okay, so in practice, you can use unsequential, which is give you just put the layers n and get everything for you. But if you have logic, you have a lot of fancy logic to do in the forward function, actually you can use the n block to implement by your own. And the benefit here that it's easy to debug. For example, I can use y equals to, I want to get the internal results. I can let self to x, and I can print internal result and returns self dense. So, which means you can debugging at the internal results. It's much flexible. You can do a lot of things there. Okay.